So here are some methods that rely on these cluster-based approaches or instance-based approaches. The first one here is PROCUS, which is a cluster-based approach. So we learn the subspace preference for each cluster from the full dimensional case. The cluster model itself is k-medoid based, so, or k-means, but it uses medoids, not the means. So the clusters are represented by the medoids, and to each cluster there is assigned a subspace, which is the set of relevant attributes. So the projection in which the cluster actually somehow lives, yeah, or is accommodated. Where this cluster is most significant, so to say. Yeah. And each point is again assigned to the nearest medoids, and in that case the distance to each medoid is based on the corresponding subspace of the medoid. Yeah? So if, for example, the medoid of this cluster here is only somehow existent in this subspace, points are projected into the subspace, and then the distance to the medoid is computed. Yeah? And the same holds true for this for the medoid of this cluster here, where all points are projected on this subspace, and then the distance to the medoid is computed for this in this subspace for this cluster. Yeah? And then of course the points belong to that cluster with the closest medoid, as you know from partitioning-based clustering. Yeah, and since a lot of things can go wrong here with these projections, the authors of PROCUS have somehow tried to accommodate also noise. So points that have a large distance to the nearest medoid are classified as noise. Large means typically you apply a threshold, and if points are far apart to the nearest medoids than this threshold, they are classified as noise. Yeah, the whole thing is a three-phase algorithm, so 3 steps actually. The input parameters is, as always, the number of clusters, k, and then the average dimensionality of subspaces L. So you have to tell the algorithm not only the number of clusters, but also somehow the average dimensionality of the subspaces. That doesn't mean that all of the clusters need to be in the same dimensional subspace, but I would say more or less. Yeah. Okay, the first phase is just the initialization phase of cluster medoids. In that case, they try to somehow spread the centroids or the medoids all over. So we want to, of course, have not centroids but medoids from different clusters. Since we do not know which are those k points, we want to have k medoids in the first glance. We choose a superset of b times k medoids, which is called M here. So M is a set of b times k points, potential medoids, so that they are well separated. And how do they do that? Well, they choose a random sample of a times k data points. Then out of this sample, they select b times k points by greedy selection. And the greedy criterion here is that medoids are picked iteratively so that the current medoid is well separated from the medoids that have been chosen so far. So you have already chosen maybe 5 medoids, and then the 6th medoid will be chosen such from this set here, such that it is the one that has the highest distance to the already chosen medoid so far. Yeah. The additional 2 input parameters A and B are just introduced for performance reasons. Of course, you could do that on the whole data set instead of a random sample, but of course you don't want to do that, obviously. Yeah. So the whole thing is just, it's just another idea of how to initialize medoids for partitioning and clustering algorithms. So don't overemphasize this one here. Yeah. Yeah. So as stated here, this procedure has nothing to do with subspace and projected clustering. Could also be applied to any k partitioning algorithm, k means whatever, yeah, in the full dimensional space. No worries. So the real subspace clustering or projected clustering algorithm actually starts in step 2, which is an iterative phase working similar to any k-medoid clustering, and here you try to refine the original medoids you have gained from step 1. Yeah, so now you want to refine them, well, how do you do that? Well, you randomly choose k medoids from phase 1, from step 1 as initial medoids, and then you replace the bad medoids, whatever that means, with other points from this sample M here. Yeah, as long as the quality of the clustering increases, of course. Yeah, and how to replace that? Well, you find dimensions related to the medoids. We will have a closer look on that. Assign data points to the medoids, as already sketched a little bit, but we will talk about that also. Evaluate the clusters formed, coming up, and then find the bad medoids and try to improve the results by replacing them with other candidate medoids from this set here. So what you generate here with this b times k points actually is a set of candidate medoids, which you then just shuffle around in step 2 in order to find the best k medoids from those candidate medoids actually. Yeah. So how to find the cluster dimensions? Well, for each medoid, you apply a distance threshold of delta, actually 2 delta. Yeah, this is actually the distance to its closest medoid. Yeah, so you have a medoid M1 here, and you have a medoid M2 here. Those orange things here. Yeah, and the distance between those two is 2 times delta. Yeah, and you say that delta is the locality of this one here. Yeah, so this M2 may have a different delta because there may be other medoids being closer to M2 than M1. But anyway, so for M1, M2 is the closest medoid. So half of the distance between those two is delta, and delta defines the locality of M1. Everything every point that is within this delta here will be assigned to M1 and not to anything else. Yeah, so that is the locality. And the intuition is that well, each medoid we want to associate with those dimensions where the points are close to the medoid in those dimensions. So we compute the average distance along each dimension from the points in the locality of this M1 here. Yeah, and then we calculate for the medoid the mean and the standard deviation of these average distances here. And then we somehow calculate another value, which is actually, well, the actual distances, the average distance minus the mean times the standard deviation. Yeah, and that gives you a kind of measure. The smaller it is, the better it is, obviously. Yeah. So we choose k times L smallest values from those dimensions here, from those values here, with at least 2 chosen for each medoid, which is some magic number here, but that means that at least 2 features are relevant for all medoids. And at most it's k times L, so to say. Yeah, yeah, that's it. And the output is a set of k medoids and their associated dimensions that you took. Well, you took here the k times L smallest dimensions, which are then associated to the medoid. Yeah, and that is actually computed for the locality. So once again, well, you compute the locality, and from the points in the locality, you take those features, original features. Yeah, we are in the extraspiral setting. You take those features where the locality has a small variance actually. Yeah, so you take the k times L smallest features with the smallest variance here. Yeah, that's the idea. Then the assignment, as I told you before, we use, or the authors propose to use only those features that are relevant to each cluster. So each data point is assigned to the closest medoid using Manhattan, so-called Manhattan segmental distance. So only the relevant dimensions of the corresponding medoid counts. Yeah. So here's the Manhattan segmental distance for any 2 points, x1 and x2. in any set of dimensions, you only look at those dimensions here. And those dimensions are the relevant dimensions of the corresponding medoid. So one of those things is the medoid, and the other is a data point, and then you can and the d is the dimension from the medoid, computed here in the first step. And then you evaluate a cluster using average Manhattan segmental distance from the points in the clusters to the centroid. So that is the usual thing you do, and you replace bad medoids with random points from M. So points that have a large average MS dist of their points, which means they are not compact, but they are the spread is too large. You replace them with random points from M. And the whole thing terminates if the clustering quality does not increase after a given number of current medoids have been exchanged. So you restrict the replacements by another parameter, actually. So there is another hidden parameter in that criterion saying when to stop, actually. And then in the last step, you also do a refinement. So in the end, you reassign subspaces to medoids as above, as we just outlined here. But you only use those points assigned to each cluster rather than the locality of each cluster. So originally in the refinement in the second phase, we always use only the locality of the medoids in order to compute their preference, their preferences. And now for the refinement step, you use the entire cluster members from the last iteration, so to say. And then you again reassign the points to the medoids, and points that are not in the locality of any medoid are classified as noise. So you have a kind of noise sensibility in that one here.